Okay, things are about to get very, very interesting indeed, so I hope you've got some good listening skills, because this is going to take some serious intelligence for you to understand this. So let's get started. How astronomers, not how I do it, but how astronomers measure the distance to stars. Okay, this is not what I agree with, this is just what physics teaches. Okay, so let's start off with the sun here. Okay, and we're going to have a distant star round about there. Okay, we want to measure the distance to that star. Now they say, they rest on the assumption that the Earth is going around the sun. That's the first problem. Okay, so there we go, they're resting on this assumption that we've got this parallax shift, this change that's going to occur. So we've got this angle here, then we've got angle number 2, the 2 points of parallax change. Okay, now what we've also got is we've got a distance here, and we're going to call that d, which is what astronomers say. This is assumption number 2. They say that it is 1 astronomical unit. Okay, now 1 astronomical unit is 93 million miles, but before we do that, let's just move on. What they're going to do, let's just put that, now the distance in between, we're going to call that d. Okay, we'll call that big D, we'll call that little d. Right, there's a fixed point in space here, and there's also another fixed point in space up there as well. Okay, so we've got this angle here, which is theta, which is also this angle here, which is theta. And we also have a right angle here, which is 90. Okay, so what we're interested in is we're interested in a shift of these 2 angles here. Okay, like so. So what we're going to do is we're going to define 1 AU. 1 AU equals 93 million miles. Okay, 1 AU equals 93 million miles. Okay, now look, let's see what we've got. We know that tan is opposite over adjacent. Okay, opposite over adjacent. So we got tan 90 minus theta, as you can see there in the corner, equals big D over little d. Right? Okay, big D equals d tan 90 minus theta. D equals 26 trillion, because that's how close the nearest nearest star or star is in distance. And then we've got d over d, okay, which actually equals 1 arc second. Now, what on earth does that mean, you probably think? Well, very difficult to explain unless you're a mathematician, but well, what we've actually calculated is we've calculated a shift from the observer's point of view, whereas if the centre is overhead, and these are all galaxies and stars, etc., all around you, what we're trying to calculate is we're trying to calculate the shift, which supposedly will move 1 arc second. So there should be a slight shift of a star moving across the sky, but in order for this to be carried out correctly, when the observations are made both here in January and July, 6 months apart, you have to wait for the time when the sky is exactly the same from an observer's point of view. Okay, you have to wait for that constellation to come round where the Pleiades are in the exact part of the sky as they were in the previous observation. Okay, now let's explain things a little bit about what I mean by 1 arc second. What you've got is you've got 1 degree equals 60 minutes, okay, arc minutes. Then you've got 1 arc minute, 1 arc min equals 60 arc seconds. then you've got 1 degree equals 3,600 arc seconds. Okay, so 1 arc second, 1 arc second equals 1 out of 3,600 of a degree, that is. Oh, I love maths. Okay, so the distance to D equals 1 parsec, which equals 3.46 light years, or it's the same as 206,000 AUs, or astronomical units. So that's 206,000 times 93 million miles. And that is the mechanism used by physics to determine star parallax. So you can get an idea of the scale of it looking at this drawing. This distance here, for this to be to scale, that has to be 206,000 times 93 million miles. And that's how you would work out the parallax using standard physics. Now remember, this rested on the assumption that the Earth is spinning round here from this observation. It rested on the assumption that we knew the distance to the Sun as 1 astronomical unit being equal to 93 million miles, which really kind of debunks the whole of physics in my opinion, because when I learnt this we were told that you had to assume the astronomical unit of 93 million miles. I've already calculated the distance to the Sun on the flat Earth, and it was something like 3,600 plus nautical miles, which really just kind of debunks everything, doesn't it? Now, it's interesting because I was indoctrinated and I learnt all this stuff, but really, the calculations are perfect, but if you're plugging in the incorrect figures, you're going to come out with gibberish. Everything that I've written here is completely correct, except the assumptions that it rests upon. I rest my case. Another goal for the Flat Earth model. Let's move on to our next examples. Now, ladies and gents, you are going to get people that are going to try to contest what I have just illustrated with the phony, fanciful argument that the stars are so far away that the parallax cannot be detected. Well, guess what, smarty pants? I have got the solution to how you will respond to that nonsense. What you will simply say is, why don't you go outside and look at the stars at night time, shut one eye and look at the stars and close the other eye. Then open that eye, shut the other eye, and keep flicking back and forth, looking at a bright star. And you will notice that the bright star will in fact move from your position. The reason why it will do this is because those stars are very close. The Earth is not spinning. If the Earth was spinning, you would see a parallax change between January and July that would be monstrous. If you can detect a parallax change with your own eye on one star in the sky, when your eyes are just 2, 3, maybe 4 inches apart, there should be an absolutely monumental parallax change between January and July. We don't see it, ladies and gents. We don't see it because the Earth is geocentric. This is very, very profound evidence to show that. If you don't understand anything that I've said, send me an email and I'll help you out. But what I've just illustrated here is not nonsense. You can go out for yourself and legitimize the experiment by staring at the stars. The same as you can shut one eye and look at your finger, you'll notice a parallax shift, and because your finger is very close, you'll notice that the movement is substantial. The star movement won't be as substantial, but it will be apparent. Okay? because you're moving that point of the observer, your vantage point. We never move the vantage point in space. We can't, because the Earth is geocentric. Thank you very much. Hope you enjoyed the video, and I'll see you again. You are the real heroes out there, the people that watch the videos, and I appreciate everybody and all their support.